everyone, I'm Dr. Jing Liu from Shanghai University Medical College. Today, we will continue the discussion on respiratory physiology. Last session, we talked about gas exchange in the lungs. The oxygen in the blood has to be carried to the target organs and tissues for further gas exchange. So today, we will focus on the transport of oxygen and carbon dioxide in the blood. In China, carbon monoxide poisoning occurs every year, especially in winter. Why is it fatal? How do we treat it? After this session, you will have the answers. Here are the learning objectives. When finishing today, you will be able to describe the forms in which oxygen is transported in the blood and explain the physiological significance of hemoglobin oxygen dissociation curve and the factors that affect it. Gases are carried in two forms during the transport: physically dissolved and chemically bound. For O2, most of it is bound to hemoglobin, and the rest dissolved in plasma. The pressure of O2 in the blood is the most important factor affecting the bonding between O2 and hemoglobin. Interestingly, the association of O2 with hemoglobin is a favorable factor. So the bound O2 will facilitate further O2 bonding. This picture shows the relationship between the pressure of O2 and the percentage of oxygenated hemoglobin, called hemoglobin oxygen dissociation curve. It is not a straight line. At the top part, high O2 promotes its bonding with hemoglobin, and at the bottom part, the O2 pressure is low, favoring dissociation of O2 from hemoglobin. Therefore, the curve becomes S-shaped. Before further description of the curve, let's introduce some concepts first. Oxygen capacity is the maximum amount of O2 that can bond with hemoglobin. Oxygen content is the actual amount of O2 bound to hemoglobin. And the content divided by the capacity is called oxygen saturation. The higher the pressure of O2, the higher is the O2 saturation. Let's go back to the curve. The relative flat upper part reflects the high O2 pressure in the lungs, promoting the bonding of O2 to hemoglobin. In this range, the O2 saturation changes relatively slightly with large fluctuation in O2 pressure from 60 to 100 mmHg. This mechanism can prevent hypoxemia as long as the pressure of O2 is greater than 60. This is particularly important in situations such as high altitude or diving, where O2 pressure is low. The middle part of the curve is relatively steep. In the range of O2 pressure from 40 to 60, the bonding ability is decreased to promote the dissociation of O2 from hemoglobin. So the freed O2 can be used by the tissues. The bottom part of the curve is very steep, making O2 even more readily available for the increased tissue demand, such as during exercise. Now we understand what the oxygen dissociation curve means. Is it constant, or will it change under different conditions? What factors that will have an impact? The most important one must be the pressure of O2, as we just discussed. Interestingly, the pressure of CO2 and pH of the blood also affect the curve. The increased pressure of CO2 causing a decrease in pH will suppress the bonding ability of O2 to hemoglobin, leading to more free O2 and lower O2 saturation. So the oxygen dissociation curve will shift to the right. For example, in tissues, consumption of O2 will produce more CO2 and help the dissociation of O2. In contrast, the pressure of CO2 in the lungs is lower, with a higher pH, facilitating the binding of O2 to hemoglobin, moving the dissociation curve to the left. Another modifying factor is temperature. An increased temperature promotes the activity and amount of hydrogen ions through its influence on metabolism. Increased metabolism also produces more CO2, so the temperature affects the O2 binding to hemoglobin through direct and indirect ways, and finally causes decreased hemoglobin affinity for O2 and shifts the curve to the right. On the contrary, a lower temperature will suppress the activities of hydrogen ions, promotes the association of oxygen with hemoglobin, and shifts the curves to the left. During the metabolic process, a byproduct of glycolysis in red blood cell, 2,3-BPG, can bind to hemoglobin, and this will decrease the O2 binding to hemoglobin and shift the curve to the right. Consequently, more O2 is released to the tissues. This physiological function is very important under low O2 pressure. For example, at high altitude, low atmospheric O2 levels increase the anaerobic metabolism with increased 2,3-BPG levels in order to supply more O2 to vital organs and tissues. Let's have a brief summary here. The factors that influence the oxygen dissociation curve include partial pressure of O2 and CO2, blood pH, temperature, and the 2,3-BPG levels. All the factors are related and all aim to supply enough O2 to the tissues to support your daily activities under different conditions. How about carbon monoxide, CO, we mentioned at the beginning? Actually, excess CO is not found under normal conditions. Incomplete combustion produces more CO, which has higher affinity for hemoglobin than O2 at the same binding site. Even worse, the binding of CO to hemoglobin is also facilitated by the amount radiabound. So in a sealed environment, the pressure of CO will increase gradually with incomplete combustion, causing CO poisoning. The patient may eventually die from hypoxia. Therefore, in treating such patients, a hyperbaric oxygen chamber will be useful. The high O2 pressure will displace the bound CO molecules from the hemoglobin, which can in turn bind CO. Okay, today we have introduced the transport of gases in the blood. Although O2 is transported in two forms, most is bound to hemoglobin. The pressure of O2 is the most important factor influencing the binding of O2 to hemoglobin, forming the oxygen dissociation curve, which can shift under different conditions. Here are the references. That's all for today. Thank you and see you next time.